Good morning all. Just waiting for the system to get itself going and everything to work, and then we'll be kicking off. I think it's looks as if we're there. So good morning everyone. Hello, I'm Phil Archer from W3C. I'm not going to be saying much in this webinar other than to introduce the speakers. So we'll be doing that very shortly. And obviously you're very welcome to join this second technical webinar of the Big Data Europe project, and we're going to be hearing all about Flink very shortly. But just before we do that, I'm going to ask Hajira Jabin to give us an overview, just a very quick introduction to Big Data Europe before we hand over to Kostas Tzoumas. So Hajira, when you're ready, please.
Hello everyone, and thank you for joining this webinar. I'm Hajira from University of Bonn, and as Phil said, I will very briefly present the Big Data in Europe project and the platform that we've built. BDE is a Horizon 2020 Coordination and Support Action project, which started in 2015. We are in the second half of the second year at the moment. The objectives of the Big Data in Europe project is to address the big data needs of the 7 societal challenge domains, which are health, food, energy, transport, climate, social sciences, and security. The challenge that we want to handle here in Big Data in Europe project is the lack of data science skills. So we want to lower the barrier of using the big data technologies and lower the level of effort and skills required to get started with these big data tools and workflows. So we want to establish the cross-societal challenges, cross-domain data value chains, and to assist in working in any sub-part of these value chains as well, using the big data technologies. In coordination, we are engaged with the stakeholders, and we elucidate our requirements using the workshops and various other methods. This is the coordination part of the project, and in support, we are creating a big data aggregator platform. We have more than 16 members from across all the Europe in this project. 9 of these are associated with the coordination role, associated with the 7 societal challenges, and 7 of them have the technical support role in this project. Working within this project is going as follows. We are raising awareness and engagements with the stakeholders across the 7 societal challenges through multiple workshops and some surveys. We gather these requirements through surveys and through these workshops and creating domain-specific databases, which are then showcased in the BDE platform. The evaluation of BDE platform is being done through the 7 pilot cases of these societal challenges. The architecture of the platform is something like this. We have chosen Docker as a deployment tool, which is a very lightweight visualization tool, which allows us to bundle all the dependencies in one Docker. The Docker file acts as a template to use one of these components. And in order to deploy these components, big data components at scale or within cluster, we are using Docker Swarm. Docker Swarm allows us to create clusters of Docker component and enables us to link different Dockers together to create networking among these Dockers, to have a resource organization among different Dockers, and fault tolerance of the cluster. The technical aim of the BDE project is to reuse the components wherever possible, and we build something if it's not available. For example, Docker Compose up or Docker Compose allows us to create multiple Dockers at one time. However, one thing that we found missing here is to have an execution workflow of different components. For example, in order to get started with Flink, you want to have HDFS cluster up and running before a Flink worker would try to read from HDFS. Similarly, a Flink worker trying to connect with a Flink master needs to have Flink master up and running before worker tries to connect with it. So we have created an init daemon which allows us to create such a workflow at scale. Similarly, different components like Spark or Flink or HDFS and many other big data tools, they have their own user interfaces. So we have created an integrator user interface where all of them are bundled together under different tabs. At the same time, we have user interfaces for pipeline monitoring and SOM user interface as well. So these are the very overview of the features that we have in the BDE architecture. So it does not mean that one must install this intermediate layer. You can simply choose not to install this intermediate layer if you're not interested in workflows. You can choose any of the component that you want to start working with and install it. So BDE has a very nice plug-and-play-like feature of different components. For installation of this platform, we have different guidelines present on our GitHub page. You can install using manual guideline or the Docker machine. There are also screencasts present in the YouTube channel. So this was the very brief overview of the BDE project and the architecture. Thank you very much.
Thank you, Hajira. I just want to say a couple of things. If you have questions, please put them in the question box that you should be able to see on your screen. Our colleague Mohammed is going to be collecting those, and we will come to those at the end. So do please write your questions down at any time, and we will organize that, and we'll get to those at the end of the webinar. In the meantime, I'd like to ask Thomas if you can switch over to Kostas' screen, or if you can, Hajira, if you stop sharing and Kostas takes over. We're very grateful and very pleased to welcome Kostas Tzoumas, who, as you can see, is from dataArtisans. We're very grateful to Kostas for giving us the time today. This is really the central point of our webinar this morning, who's going to tell us all about Flink, what's going on, what it's used for, and so on. So Kostas, thank you very much, and over to you.
Hey, thanks a lot for having me. So I'm Kostas. I've been working on Flink for about 5 years. I was an academic myself, and 2 years ago I started together with my co-founder Stefan and a bunch of other folks, dataArtisans. dataArtisans is really the company that is sort of behind Apache Flink. So most of the active Flink committers are dataArtisans, and I'm the original creators of the framework. And it is our mission to continue to grow the Flink community, continue working with large-scale Flink users and make them successful. And we are also providing the DA platform, which is a distribution of Apache Flink that comes with enterprise support and is QA'd by dataArtisans. So what I would like to talk about today is the following. So first of all, why Flink, right? Why does this project exist, and what sort of gap does it fill in the industry? Next is an update of what's happening in the Flink communities, in particular, who is using Flink, what are people using it for, and what is coming up next. And finally, if I have time, I would like to continue with a broader vision on Flink. So the motivation from all this is what we call the streaming architecture. So, you know, every once in a while we see a re-architecture of the data infrastructure stack, and we are seeing this right now, and it is based on what we call streaming or streams of events. And there are many drivers for that. So one big driver is better isolation of applications. This is connected with the whole trend around microservices, where instead of trying to hold the state of the business as a whole, every application is maintaining its local state. And the way to connect these applications, these microservices, is using data streams. The next driver is, of course, the never-ending quest for lower latency. So many businesses, it is crucial for many businesses to have more real-time reaction to what is happening. So monitor the users, monitor the app usage, monitor the infrastructure in real time, and be able to react to these events in real time. The next is building continuous applications robustly. So there are all of these applications that exist in every company that are running 24/7. They are processing data, so they're ingesting data, processing data, and then either powering a live application or powering a dashboard, or further pushing the data to some other system. But the important thing there is that these applications need to run 24/7 robustly, and there are millions of ways to implement those. So many of those are just implemented using like just Java applications. Many companies have built their own, let's say, message exchange or streaming platform internally to implement those. Others implement those using Hadoop, or let's say repeating Hadoop jobs that wait for some data to be gathered, and then they fire a Hadoop job. And the point here is that streaming technology is actually the best way to implement these applications. And finally, another driver is to unify what we call real-time data and historical data. So all of these lead to some kind of architecture that looks similar to this. So this is what we see every day. Events on the left from a variety of sources are gathered. Usually people employ a message queue, and usually that is Kafka, which is basically a log, an event log, that serves as the ground truth, let's say, for the company. So if you want to get to know something about the company, you need to replay this log of events and create what you want to find out. And this is exactly the point of local application state. So the next step here is compute. So this is kind of the storage part, and this is the compute part for streaming, where you have a multitude of Flink applications that consume these event streams, and they maintain local application state. And the fact that the application state is local and it's not global makes things way easier to manage. And then we have a serving layer and a storage layer. So some event streams may be archived to Hadoop, some event streams may end up in a database like Cassandra for querying. Interestingly, there is work underway in Flink to add the ability to query Flink state directly without having to go through a database or a key value store for that. Or other results of these applications may end up as the write streams back in Kafka to be consumed by other applications, other teams, etc. All right. So Flink in this architecture is sort of the compute part of the whole infrastructure. So any kind of computation that you want to do on data streams, that is Flink. So the next question is why Flink, right? So there are actually a number of stream processors out there. A lot of them are open source, and we're actually seeing new ones coming every day. So if I had to summarize it in one slide, it's the following. So in my opinion, before Flink, users of stream processing frameworks had actually had to make hard choices, and they had to navigate some pretty tough trade-offs. And in particular, a trade-off between what is the volume of streams that I can handle, what is the latency that I can achieve in my application, and what is the accuracy that I can achieve in my application. So usually you could get one of the three or two of the three, but never three of the three. And that was the reason that people invented things like the Lambda architecture to combine streaming and batch technology to get accuracy, etc. But the point is that with Flink, you no longer have this trade-off. Yeah. So Flink eliminates this trade-off. We have clocked Flink to tens of millions of events per second for stateful applications. That was actually in a very small cluster, 10 nodes. At the same time, Flink can scale to thousands of nodes. That is happening in production right now, for example, at Alibaba. You can get sub-second latency, and you can tune that as low as single-digit milliseconds for your application. And you can get accurate computation results under a variety of scenarios. So you can get accuracy under failures. This is what Flink does with its checkpointing mechanism. You can get accurate results under downtime, so not only unplanned downtime, it's failures, but also planned downtime. And you can get accurate results when the input streams are out of order. So when we have what is called the event time skew, when elements arrive late or they don't arrive in the order that they were produced. And let me dig a little bit deeper into all of this. Yeah. So the first thing is stateful streaming. What I mean by stateful streaming is the following. So stateless streaming, to begin with, are basically stream transformations like filters or mappers, where you get an event, you do something with this event and this event only, and then you emit another event. So the output only depends on the input. In stateful streaming, the output depends on the last event and potentially every event that has happened so far. So operators there keep state. And if you see at the evolution of stream processing frameworks in the open source space, we started with stateless streaming, which was Storm. Then we had stateful streaming, which was introduced by Samza. And what Flink introduced was accurate stateful streaming. So in my opinion, stateless streaming, I mean, there are some applications that are stateless, but most interesting applications are stateful. And stateless streaming just pushes the problem to the application. So at some point, you need to maintain state. What Flink provides with accurate stateful streaming is that we no longer need this lambda architecture. So we no longer need a layer that will produce an extra layer that will produce the accurate results. A streaming layer can do that, and basically you get a lot more tools to develop your application. So you don't have to worry about keeping state and removing duplicates in the application. So you just get much richer tools to develop applications. The way Flink does that is with a mechanism called checkpoints. Very briefly, what that is a mechanism to take snapshots of the application state. These snapshots are consistent in the sense that there's no data loss and there are no duplicates in the state. And they are also asynchronous in the sense that the computation, like the actual work, never stops. So the snapshot mechanism is overlaid to the regular data processing. And that provides exactly once state guarantees under failures. The way it's done is by injecting special records that are called barriers in the stream that sort of signify a logical time and logically separate the stream into something that will be snapshotted in the next checkpoint and something that will not be part of the next checkpoint. The details of that have been published. There are research papers about this, and there's a lot of information on the Flink website. The cool thing about checkpoints is that they can actually double as a mechanism to do transactions across systems. One thing is to have exactly once guarantees of Flink state. Another thing is to actually have exactly once guarantees end-to-end from the whole pipeline of systems, as you mentioned before. So we have, for example, here Kafka, Flink, and HDFS, right? So how can we guarantee that this whole pipeline is exactly once end-to-end? So the way that we can do this with Flink is by writing sources and sync operators that are actually stateful Flink operators that take part themselves in this checkpointing mechanism. So for example, what is already there in Flink is an HDFS sync that guarantees exactly once. So you can move data from Kafka to HDFS using Flink with exactly one semantics. And the next cool thing is that this same checkpoint mechanism actually triples as a mechanism to version state, which we call save points. So what this gives you as a user is the ability to manually snapshot applications when you want from the command line, and essentially go back and forth in time in your applications and while maintaining state consistency. You can also do things like, so we have a version 0 here of an application, and we take a save point at T1, and then we're actually forking a different version of the application. So you can actually version applications consistently. So what that gives you is easier code upgrades, both application and Flink, maintenance. So let's say you want to move to a different cluster, better debugging. You can do things like A/B tests, what-if simulations, etc. So in practice, this is actually absolutely necessary to manage streaming applications in production. And the next thing, besides, so we mentioned accuracy in the case of failures and accuracy in the case of downtime. The next thing is accuracy in the case of out-of-order streams, or when the input stream, the events in the input stream are not arriving in the order that they were produced. So the way that Flink does that is by what we call event time streaming. So this is based largely on the work of the Google Dataflow folks, which is now Apache Beam. So the semantics there are very similar. This slide is the easiest slide that I have come up with to describe the notion of event time streaming. So the order that events happen in real life. So let's say here in Star Wars, the order that events happened in Star Wars is not the order that the movies were rolled out in the cinema, which is called processing time. So Flink basically gives you the tools to reason about event time and processing time, which is exactly what you need to get accuracy under event time skew. This is done by a mechanism that's called watermarks. There's also a lot more information online about that. But basically what you get is that you get a handle on the accuracy versus latency trade-off. The results of the computation do not depend on what time you're executing the computation, so the results of the computation depend on only on the event stream, which also gives you the ability to do stream reprocessing to rerun an application later. And the main thing in Flink, the main innovation here is that the mechanism of windows and the mechanism of checkpoints are very different. So you can have checkpoints every 5 seconds, and that does not restrict you in what kind of windows you can define. So you can define session windows, any kind of sort of complicated ways to group your events by that time. And in general, what we see is that there are two emerging models for programming applications on streams. One is the model around event time and windows, which was started by Google Dataflow, and which is what Flink has as well. Now Dataflow is called Apache Beam. And there the main thing, that's a lower level API, you have a lot of control over the stream. And the main thing is that you can separate the what do you want to do, where in event time, when processing time, and how. And the other model, which is something that the Flink community is working on right now, together with the Apache Cluster community, is SQL queries on structure streams. So there, the main idea is that a stream, it can be just a changelog of a table. So you can see a stream as a changing table, and you can see a changing table as a changelog, which is a stream. So based on that duality, we can actually have SQL now on streams, not on static tables. In my opinion, both of these models are very useful, and Flink will actually support both of them. One is lower level when you need full control, the other is higher level when you want to write SQL. So just in summary, the main thing that Flink brought to the industry is the following. So having a framework that you can depend on, that provides you the accuracy, the performance, etc., actually makes it easier to move more stateful applications from a variety of different places to a data streaming architecture. So this is the main thing here. All right. So how is Flink being used? So the Flink community, so Flink became an Apache incubator project in April 2014. It became an Apache top-level project in December of the same year, 2014. And since then, the community has been growing very, very fast. So this slide is probably already outdated. So there are more than 220 contributors right now, people that have contributed code to the system. The last release had 95 contributors. There are about 40 meetups around the world, user groups on Apache Flink. 2015 saw a 2x to 3x growth in various metrics in the Flink community, and we expect a similar growth actually in 2016. There's a number of companies that are using Flink in production at very large scale. These are some of them. You can see a lot more at the Flink website, at the Powered by Flink page on the Flink website. And they are actually doing quite sophisticated stuff with Flink. So these are just three examples that sort of highlight the scale at which Flink is being deployed in various dimensions. So the first is Alibaba, the largest e-commerce company in China. So Alibaba is running Flink. They're running a system that is based on Flink. They call it Flink, that powers the recommendations behind Alibaba search. The largest job that they're running has more than 20 operators. It's running on a cluster of 1,000 nodes, and it's actually processing millions of events per second, and it is very useful in the company's bottom line. King is a company that develops mobile games, including Candy Crush games. So here, what is very interesting is the scale, not in terms of number of nodes, but in terms of state that is being kept. So King has developed a system, they call it Arbea, where they give access to stream processing internally to their data scientists. That is powered internally by Flink. And there they have jobs that are actually maintaining hundreds of gigabytes of state 24/7 with exactly one guarantees. And the third example is Bouygues Telecom. That's the third largest telecom carrier in France. And here the dimension that I'm picking is how long have you been running it for? Yeah. So Bouygues is running about 30 Flink applications in production, and the oldest application is actually more than a year old, running 24/7, and they are processing 10 billion events daily. That is actually a fun thing. This is the control room of this telecom carrier in Paris, where they are monitoring the signal, the mobile signal, and the landline signal in France. So there are people actually sitting in this room, and they're looking at how the signal develops. And this is internally powered by Flink. A few weeks ago, there was Flink Forward. Flink Forward is the annual Flink conference. Flink Forward 2016 was the second one. It was held in September in Berlin. And these are just some of the organizations that came there to speak about how they're using Flink, how they're contributing to Flink, how they are building systems based on Flink, etc. So large companies from several verticals from all over the world, Europe, US, Asia. All right, let me skip this one. So what is happening in Flink right now, and what should we expect to see? So this is basically the main things that came, the main new things that came with the last Flink release, Flink 1.1. So a bunch of more connectors, in particular to Kinesis and Cassandra, a metric system, the first version of SQL on streams, session windows, and enhancements to the libraries, in particular the CP library. And if you actually take that and combine it with the work that is actually currently underway in Flink, you get that. So there's a lot that is happening in many areas. If I had to sort of divide it in a few areas, the following. So there's a lot of work. There's work happening in sort of connecting Flink with the wider big data and DevOps ecosystem. So a prominent thing here is integration with Apache Mesos that should come in the next Flink release. There is work that is happening to make Flink accessible to a broader audience of data scientists and data analysts that don't speak Java or Scala. And this is in particular the work on Stream SQL, defining Stream SQL, Stream SQL semantics, and implementing that in Flink. There is work that is happening in the application domain, so features that enable you to write more applications easier, so things like variable states, site inputs and outputs, and session windows. But the bulk of the work is actually happening in the operations department. So, and this is largely driven from large organizations that are deploying Flink in production. So there we have things like security, authentication, dynamic scaling, compatibility of safe points with checkpoints, maintaining very large scale, etc., etc. So basically the message here is that as Flink is being deployed right now at some of the biggest stream processing infrastructures of the world, a lot of the work in the community is about making it operational there, so it's around operations. All right. So I don't think I have much time, but let me just finish up with my personal vision, so what I see Flink developing to. So when we talk about stream processing nowadays, we usually talk about real-time applications or near real-time applications, and the technology to cover those is basically, let's say, low latency streaming. So this is what we've been talking about so far. But that is just the tip of the iceberg for data streaming. Other applications that are a perfect fit for streaming technology is continuous applications that are not necessarily real-time. So we can call that high latency streaming, and it is as beneficial as low latency streaming. Analytics on historical data, so that is covered by what we call nowadays sort of batch processing, but there's no real reason to not analyze historical data using a stream processor. It is actually, it can actually be better and easier to use one system for both. And the final is request response applications, applications that query databases, and these are very interesting for stream processing, especially when we talk about large state in the stream processor that is queryable from the outside. So a few words about these robust continuous applications. I touched upon this. These are, for example, this is such an application. We're gathering some data, we're putting it in a file, we're firing a Hadoop job, and we're putting the results somewhere. Then some new data comes, so we have a scheduler that is scheduling these Hadoop jobs. We're putting data in a new file, etc., etc. So this is quite complicated. It is very fragile. Things can go wrong everywhere. It's very hard to maintain and change this application. A much better way to do that is with a streaming job, and that does not have to be real time. In particular, there are streams that are low latency streams, so think of Kafka partitions, and there are streams that are high latency streams. Think of rolling files, as we saw before, and both of these are a great match for stream processing. And in this context, where everything is a stream, batch processing is just analyzing the bounded subset of the stream, so just starting from a begin time and ending to an end time. And then both of these can be done very well with stream processor. We skip that one for time. And the final kind of applications that I talked about was request response applications. So here, a typical stream processing architecture has, as I mentioned, a message queue, let's say Kafka, a stream processor that maintains the state, and that state is periodically pushed to a serving layer or a storage layer, let's say a database that is used to serve queries. So what is happening in Flink is actually the ability to hold very large state inside the stream processor and provide a query API, so these queries can be routed directly to Flink without having to go through the database. And the reason that this is interesting and useful is that moving the data from the stream processor to the database is, in the vast majority of cases, the bottleneck of this whole processing pipeline. So in summary, the streaming architecture is getting increasingly popular. It just makes so much sense to interpret continuous data as streams. This is what data really is. And it just makes it so much easier to develop applications for data. What Flink excuse me, brought to the world was a dependable stream processing framework that basically eliminates prior trade-offs. Currently, I would say the largest focus in the Flink community is operations, so lots and lots of operational features to deploy Flink in very large scale. And what I think the future will bring is actually broadening the scope of what we call stream processing beyond what we think of today of stream processing, which is sort of the real-time or near real-time applications, and broaden the scope of this to encompass a lot more applications that are currently implemented using a variety of other systems. If you want to learn more about Flink, there is a book that you can buy from O'Reilly. This is an introductory book. It's not a full-on guide. It is intended for both technical and non-technical audience, and it's about 70-80 pages, so it's not a very hard read. And that's it. If you're interested in this stuff, dataArtisans is hiring in a variety of positions. So you can visit dataartisans.com careers.
Thank you very much indeed, Kostas. It's obviously very interesting indeed. We're very grateful for that. Just to note, this whole webinar is being recorded. You can watch Kostas' presentation back again at any time. We are taking questions. If you have questions for Kostas or any of the speakers who have yet to speak, or Hajira, who did before, then please put them down. Kostas, are you able to stay with us and answer questions at the end, which is how we'd like to do it, or do we have you for another few minutes? Can we hang on to you?
Absolutely.
Great. Okay. Thank you very much. That's much appreciated. So what I'd like to do now then is, again, to remind you, please put questions in the box and we will handle those. But I'm going to now call on our colleague Gazim Sedio, who is going to tell us how Big Data Europe allows you to spin up as many Flink nodes as you want, how you can use it in our platform, which we hope is going to make it easier to do. So Thomas, if you can actually, Kostas, if you stop sharing and Mohammed and Gazim take over, then we can see Gazim's presentation on how to spin up Flink. I've got lots of questions for you later, Kostas, so hang on. All right. Okay, Gazim, over to you. If you're talking, we can't hear you.
Hello, everyone. My name is Gazim Sedio. I'm a PhD student at University of Bonn. And today I'm going to talk about how to get started with Apache Flink on the Big Data Europe platform, and mainly Dockerized version of Apache Flink. And I will show a complete pipeline demo of Flink have been used on the Big Data Europe platform. As Hajra mentioned before, on the big data scenario, there is no way to complete a single job by only one component. There needs to be a pipeline where you can combine a lot of components which they communicate by each other. And let's get a simple example as a hello world for big data, which is word count, where we need to set up HDFS in order to get or to upload any files there to do a word count execution. And after that, we need to have a Flink setup, a cluster, which we are going to set up on Big Data Europe platform or in your local environment, depends on your configuration. And after that, we need to populate data on HDFS and do a word count execution and download this data. This is a pipeline which we are going to show in a minute. And that's quite easy to do it in Big Data Europe platform. You just need to describe the pipeline on Docker Compose file and list all the images which we are provided on Big Data Europe GitHub repo, or you can have your own images. But is this enough to do just by Docker Compose up? Everyone will know that that will fail, because some of the components can be or can have dependencies between each other. So for that we came and we provide this init daemon service. We check the status of the containers, when they can start and when they can run. So for that, on the save mode, we have created a screencast for showing you this demo application, how to run.
So Jan Sierman at the Smart Data Analytics Research Group at University of Bonn. And today I'm going to show you how to get started with Apache Flink, mainly on the Dockerized version of Apache Flink provided by Big Data Europe project, and as well how the Flink is being used on Big Data Europe and how we can set up a complete pipeline where Flink is one of the components used there. Let's get started. On Big Data pipelines, there is no way to compute a single job by providing only for a single component. So for that, we will need to have a pipeline which contains a lot of components which can communicate and synchronize with each other. So let's take this simple example of word count, which make an int to set up HDFS in order to upload the file there, to do word count, and then we will need also to set up the Flink cluster, which do a computation over this file to make this word count executed. So for that, we need also to have this kind of pipelines, which we will need to set up on our Big Data Europe project. So we will have the, for each component which we are aiming to use on this pipeline, we are injected DNS entry point to show on the single user interface, which we are calling user interface integrator, which is kind of a wrapper which contains all the interfaces provided by components on the single web user interface. Let's see this web user interface. For now, it cannot be reached because there is no pipeline running. And to run a pipeline, it's quite simple. So we just need to have a Docker Compose file which contains or lists all the images provided by Big Data Europe mainly. Also, you can include your own images which may, let's say, may compute a specific job in your case. So to do that, it's simple. We just need to do a Docker Compose up to get started, and the Docker Compose creates containers which are provided on our pipeline. Let's see if now this user interface wrapper is already available. As we can see, it's up and running, which contains all the pipeline or the components which are showed on our pipeline, like Flink master, Flink worker, and as well HDFS and EQ as a file browser, Virtuoso, which will contain the data for our pipeline, and as well the monitoring of the pipeline, which we will show it in a minute. So we will see that the task manager is already connected to the job manager, and as I said before, the pipeline need to be monitored in order to know that every component which depend to each other can start in the proper way. So let's monitor our simple Flink starter demo application, which, as I said before here on this slides, it contains the HDFS, Flink cluster, the simple application which do some word count, and then we will need to set up or download the data as output from the application. By monitoring means that we will need to see if every components are working and running properly. Let's see if HDFS is up and running, and then we will finish the step on the monitoring of the pipeline. Let's open a new window because we will need them for later. Let's see if the HDFS is running. HDFS is up and running, and which contains 2 data nodes and 1 name node. And let's see if the HDFS contains any file as well. So we see that there is 1 file on input, and let's also have a look if Hue is up and running. So we need to go to the Hue single component because it will require to log in order to make it run. And we can also have upload and download files from HDFS provided by Hue. We have 1 file here, so let's make this word count running on this file, which is a README file from Apache Flink. And we have seen that the HDFS is already up and running, so we can conclude that this step can be finished. Done. We also saw that we have some data on HDFS provided by Hue, where we can upload some file, and let's conclude that this step also is finished. And now we need to see if the Flink is up and running. Flink is up and running, and then we now can start our pipeline to do a computation of the data. Let's have a look on the Flink if there is any job running. We can see now that there is no job running right now. Let's play a demo application which do a word count by starting the Flink and see the output of the data on Hue on HDFS, which contains the data over here. Output data. There is no data right now. Let's get started and do Flink to do work. Done. So we will need Flink to run this word count, and we can see that Flink right now doesn't have any job running. We need to wait a bit, and now it's running, and yeah, it's completed successfully, and word count is executed on our Flink cluster or local environment. Let's go to the previous page where we can see the file already on HDFS if there is a word count executed. So we can see that the result of the word count is there. In order to download, we need to use Hue again. And Hue provides this file browser manager to work with HDFS. So let's download this this file and see what it contains. We can see that the word count is already computed, and let's have a look for Flink. Flink have been used 30 times on this README file of Apache Flink, and by this we can argue that our pipeline is already successfully completed, and by that we mean that we can finish our pipeline monitoring. That's it from me, and please subscribe and watch what we are doing for the next upcoming screencast. Thank you.
Okay, good evening.
That's it from me.
All right, thank you very much indeed. So it's about putting it together, and the init daemon that you and Hajira have stressed is very important, so that you can see what is up and running and use Flink within a pipeline. So what I want to do now is to ask you to stop sharing and for Luigi to take over, because we want to see an actual instance of this being used, the BDE platform being used, including Flink. And again, just a reminder, if you have questions for Kazim about this, or Luigi, or for Kostas, or Hajira, please put them in the questions box, and we'll come to them just as soon as Luigi has told us about the use of the BDE platform with Flink in the transport domain. Over to you, Luigi. Thank you. Luigi? If you're talking, we can't hear you.
Oh, okay, yeah, okay.
Yep,
good morning, everyone. I'm Luigi Silmi from Ufa, and I will talk about the use of Apache Flink in the social challenge number 4, in the pilot for the social challenge number 4. So let's start. I will show. Sorry for that. So the title of the social challenge is smart, green, and integrated transport. The purpose of the social challenge is to develop a pilot in 3 different cycles where we can provide an example of the usage of the big data framework in this particular domain. So from the point of view of the objective is as I said, is to provide this platform with the big data Europe components, and the use cases are let's say that first of all the traffic monitoring, then also traffic prediction. Let's say to predict what will be the traffic in the next half an hour, and route planning also. Once we know which is the status of the traffic, we can predict also which is the fastest way to go from one point to another one. The data sources that we are currently using are 2. One is provided by CERT, that is an institution in Greece. They have a service from which more than 1,000 taxis provide data about their position during the day. And so far the data daily they have quite an interesting data set every day, and also this is the near real-time data, and they have also the historical data, because they collect all the data for 1 year. That is about 44 gigabytes. The other data set that we use is the road network from OpenStreetMap. Of course, OpenStreetMap provides other information, not only the road network, and maybe we will use also that information in the last cycle. The architecture of the platform is since we are interested in two type of data. One is the streaming for the near real-time data, and also to process the historical data. and we can also process the data from OpenStreetMap that is mostly a graph. So the idea is to build a data producer, for example, a producer that can take the near real-time data, put the data into the message broker, where a consumer, for example, a Flink job in our case, can process the data. In our case, one very important type of processment is the map matching, because we need to map the data from the taxi that are speed and geographical coordinates to the road segment in order to understand if which is the traffic status in each road segment. Other type of processes are, for example, for training a model in order to make a prediction. So, talking about the real implementation of this component, we have chosen Kafka as the message broker. And Kafka is a distributed message system that works like a log for which every record is added one by one, and then can be consumed by other processes that are the consumer of a topic. Let's say that the minimum cluster that we can think of is a cluster with three nodes, and with 3 brokers distributed in the 3 nodes. Then, for example, we will have a partition of the topic. We will have 2 topics. One topic is for the near real-time data, another topic will be for the historical data. And the partition can be replicated in the broker in order to have to scale the system and also have a certain level of fault tolerance. Then the processment of the data will be mainly driven by Apache Flink, and the consumer will be Flink jobs that will transform for example, the data, the coordinates, and will apply the map matching algorithm or other algorithm for example, for the training of the model for the prediction. Also, in this case, we will want a cluster, for example, the same 3 nodes with the Flink master and 2 worker with the slots for the jobs. Then the last component is the data storage that in our case will be provided by Elasticsearch, because Elasticsearch is quite fast and is very easy to index geographical data. Again, for our cluster of 3 nodes, we can think of having 3 nodes with the Elasticsearch with the shard and the replica distributed on the 3 nodes. Then we have another component that is based on R, because the map matching algorithm in our case has been provided by us by CERT. and so we need also this component. Now it's pretty known that R is not very easy to use in a distributed environment. There are different framework that can be used to scale R for our purposes. In our case, we will have at least one instance of the R server in any node. So coming at the implementation, this is the same architecture but with the real components. So we have the message broker that is Kafka, then the producer, for example, the taxi data in near real time. Then we will have also taxi data from the historical data set. Then the consumer is in our case, for example, for the cycle 1 is the Flink job. And then we have Elasticsearch and also Kibana, that is the web application that is used to visualize the data that is stored in Elasticsearch. Of course, any other web application can be used to make different visualization of the data from Elasticsearch. Coming to the BDE components, as was said before, the BDE platform provides the Docker images for all the components that are used in the pilot, and the idea is to create a Docker swarm where we have the 3 nodes where we have installed Docker Engine and all the Docker images that are needed for our pilot. This is an example of a pipeline, a very basic one, that is where we have 2 data sources. One is the near real-time data from the taxi. That is a web service from which we get the data and we transform data in order for any records to be sent into a Kafka topic. The same will be done also for the historical data that will be from a file system where we will put the data into another topic, and we will use the Flink job for the map matching that will consume the data from both topics in order to add the road segment to each record. So for each record from the taxi, we will have the identifier, the speed of the taxi, the timestamp, the coordinates, and the map matching algorithm will add the road segment. And then everything will be sent to Elasticsearch using a connector from Flink to Elasticsearch. So this is just an image of the result that we have had using the first pipeline. And the future work I will show you as soon after the slides of the pilot running. And for the next step in the next cycles, we will work on historical data, and also we will try to use other data set in order to have the pilot that works not only from using the data from Thessaloniki, but also from other areas. I close this slide and I move to the virtual machine where the pilot is running. So this is real time. So as you have seen before, we have different components. One component, the producer, currently run in the by itself and is getting the data and pushing the data into the Kafka topic. And we have also the Flink job, that is the application that is doing the map matching, as you can see. And then the data from the Flink job is sent to Elasticsearch. In Elasticsearch, we have already built the schema to persist the data. And as you can see from the map, these are the counts, unique count of the road segment in each. This is showed in the as small point in the city of Thessaloniki. But as you can see here, we have the number of the time in which vehicles have been driven in any road segment. So we can have a tabular view, for example, here, and we can see the number of counts for each road segment. So we know in any of these road segment how many times a taxi went through that road segment. I want also to show you the project on GitHub, where we are implementing the Docker Compose file with all the components. As you know, there are certain dependencies within the between the components that are used in the pilot. For example, Kafka needs Zookeeper. Our Apache Flink, the Apache Flink job needs Elasticsearch and the map matching algorithm. And so there are these dependencies between the components. The components and these dependencies are that the application is orchestrated using Docker Compose and the initialization daemon that is provided by the BDE platform. So you can go here into this in the BDE GitHub repository to see how the pilot is going to be run. I think it's all from my side.
Okay,
thank you very much.
Thank you, Luigi. Okay, right. One more time, if you have questions for any of the presentations that you have heard, then please put them in the question box. My colleague Mohammed is sorting those out and filtering them and passing them on. So I want to go right back. I've got questions for most people here. I want to go right back actually to the very beginning of the webinar. Hajira, can you tell us, please, this is a question from one of our guests today, what experiences have we had with centralized platforms, or is the project really only about distributed technologies? Can you talk a bit about the balance between centralization and distribution and how those topics show themselves in BDE, please? Hajira.
Yeah, hello, can you hear me?
Yes.
So yeah, the project is essentially about big data. So we haven't looked at the centralized platform. Our emphasis was the distributed platforms. And initially we were thinking to work with Mesos as the resource distributed kernel, and we started working with it. But with time, we realized that Mesos and Marathon and Chronos, they are not very well integrated with the Dockers, because we also had decided to work with Dockers as the deployment component. So during the project's execution, Docker Swarm also matured, and it somehow serves the purposes that we were looking forward to. So with the time and development in the tools, we slowly shifted towards use of Docker Swarm.
That's interesting. Sorry, I'm going to pick up on that. Are you saying that the use of Docker actually had bigger effects on the architecture you were using? Did it mean that you did do things, apart from just putting things in Dockers, did it actually make you do things differently because of that?
Because of using Dockers?
Yeah. Did it actually affect other choices that you made? What were the ripple effects of using Docker?
Well, the other positive effect that we achieved by using Dockers is the plug-and-play feature of our platform, which may not have been really possible with the Mesos and Chronos and Marathon, as I said earlier, because for that, yes, you can Dockerize some components, but not all of them, and interlinkability is not that easy if we do go that way. So this interlinking of different components, choosing any version of Flink or any version of Spark, does not have to do anything with the underlying platform. So you can pick and play with the tools that you want to work with. And also you can plug in your own components that suit your organization, company, or that you've been using so far. You can Dockerize that component and play with it alongside the existing big data tools as well.
Okay. All right, thank you. Kostas, I know you're in a hurry, you need to go. In fact, we're going to be finishing the whole thing fairly shortly, so we'll move on. Kostas, can you explain a bit about, you made the claim that the iterative execution in Flink, is it really iterative? Is that really the case within Flink? Is it iterative execution, or is it sort of pseudo?
Iterative, you mean like iterative algorithms?
The question I have in front of me reads, I'll read it to you exactly as it says, because I must admit I'm struggling a little bit here. It says, can you explain why you claim that the iterative execution in Flink is really iterative?
Oh, so I didn't really talk about iterative execution today. There is functionality in Flink to define iterations, meaning you define an algorithm that, like a machine learning algorithm, right, or a graph algorithm that iterates over a dataset. And there are also libraries in Flink that are built on top of that. This is all based on BSP, so I'm not quite sure what is the meaning of iterative versus pseudo-iterative. But in Flink, this is a built-in operator inside the system that is based on BSP. All of this is really applicable to batch processing for now. So there's not much there in stream processing. In stream processing, the whole semantics of this is a bit different, and I think this is something that we will have to figure out in the future, like creating a time window over a stream and iterating over this time window.
Thank you. And sticking with the theme of current state and future state of Flink, is it safe to use the SQL API now, or should one use the table API functions for now and then switch to the SQL API in future?
Yeah, so actually the table API and the SQL API are backed by exactly the same backend. Yeah. So they're pretty equivalent at this point. So you can use them both. In particular, both of them are actually now being parsed by calcite, and they're using the Apache calcite logical operations. So I would say they're both equally safe to use. In SQL, what is missing for data streaming right now So the data streaming support for SQL is limited to, let's say, select projects, but there's a lot more that is coming up in the next release.
All right, thank you. And one final one. I noticed in your presentation, a little bit surprised, at no point did you make a comparison between Flink and Spark. Why should I use Flink rather than Spark?
Yeah, so Flink and Spark are actually quite different. So the main let's say sweet spot for Flink is these data streaming applications that I mentioned, where you need to define state, manage state, keep state controller, and manage the time aspect of your data, so treating your data as time series. So all of this is basically the sweet spot for Flink right now.
All right. Thank you very much indeed. I think we've come to the end of our questions. I'm just checking my screen to see if I'm... oh, there's one here, right, okay. What are the must-do things for master degree students that will start their career in big data technologies? I'm going to give Kostas a bit of a break, and I'm going to ask Luigi and maybe Gazim, who's introduced himself as doing that thing. So, Gazim, what are the must-do things for a master degree student that will start their career in big data technologies? I guess anyone can take that one.
Yeah, can you hear me?
Yep.
I think that's good days are coming for master students, so they can choose which they want to use, like Flink, and Big Data Europe is one of the main point to go, because we have a lot of big data tools already Dockerized there, and yeah, they can start by Big Data Europe, checking out, and then why not use all these technologies that we provide.
Okay, thank you. And I think this is more Hajira than anyone else. When you were considering using Docker Swarm, did you instead consider using Kubernetes, if I'm pronouncing that correctly? Kubernetes. Mateo asks. Hajira, did you consider something other than Docker Swarm?
Yeah, as I said earlier, we have considered Mesos as well, and we also looked into the existing platforms like Cloudera and Hortonworks. We have looked into that before deciding to work with Docker Swarm.
Fair enough. Okay. All right. I don't see any more questions. Last chance. I'll just remind you that this whole webinar will be available on the Big Data Europe website, big-data-europe.eu. It'll all be there. I will also post the presentation separately so you can access them one by one, and that will all be online. So, but I really want to thank Kostas one more time for taking the time and trouble to be here and make that very interesting presentation and telling us about Flink. Thanks to Hajira, Kazim, and Luigi and Mohammed for their help today, and Thomas in the background. Thank you all very much indeed. There will be future webinars on the Big Data Europe project. Please join us for those. Thank you.